any hassles? Okay. Okay, so just to set the stage for this, I just want to say what I mean by the word auto-tuning. Auto-tuning is something that's pretty widely used. Many people talk about it. Basically, the way I interpret the term auto-tuning is any kind of a system that is looking through a search space of different program variants and trying to find a high-performance version of code in that search space. And typically, because these search spaces are very, very large, like it would not be unreasonable to see 2 to the power of 80 different choices. You really have to use heuristic techniques to explore that search space. So there are a number of auto-tuning systems that have been used both in research and in production. These include things like signal processing and matrix multiply, loop tiling for matrix multiply, and other kinds of loop transformations, compiler pass sequences like in milepost GCC, machine code sequences. So the area of super optimization is basically a form of auto-tuning where you're looking through different orderings of machine code. And the point here is that all of these are different search spaces where you're doing heuristic search to try and find high performance code. But one important point here is that most of these systems, probably almost all of them, have focused on relatively small pieces of code. And by far the most successful ones are the ones that are focused on particular libraries, particular library kernels in the range of a few hundred, a few thousand lines of code, like FFTW for FFTs or like Atlas for matrix multiply, which give really good performance improvements, but they really don't apply to larger applications. So the first thing that we started out looking at was to ask, can we usefully apply auto-tuning to large applications? And in particular, can we do it in a reasonable amount of time and get useful performance benefits? And the short answer, so far at least, seems to be yes, that we are able to apply practical auto-tuning techniques to fairly large applications. And we've tried applications up to a few million lines of code, but we haven't seen any bottlenecks up to that point. We think that it can scale to much larger applications as well. And this is an expensive process, so we're talking about a few hours of time. It's the kind of thing that is best done once in a while. It's not done on every compile for sure. But for example, if you're doing a simple thing, it's sort of a very brain dead, the first basic thing you could try with an auto-tuner, which is to search for different pass sequences in an optimizing compiler. We see useful speedups on applications like the spec benchmarks, but also on Clang. For example, 6.5% average speedup, and in fact, some applications go as high as 20% or 35% faster. So just to explain a little bit more how the system works, basically you can think of a compiler-based auto-tuner, so an auto-tuner that is exploring compiler-based transformations as an iterative process where you pick a point in a search space, you compile the code, you predict the performance or measure the performance for that particular code version, and then you repeat the process. And the search step there is really driven by what it is that you're tuning, what the goal of the tuner is. And that is typically some kind of plugin that is specific to the particular tuning goal that you have. And I'll come back to some examples of what we've been exploring or what you could explore with our system towards the end of the talk. So first, let me focus on the other two steps, which are the compile and the evaluate steps, and how we go about trying to make them faster. So this is a very high-level overview of the system. We call it LLVMTuner, and the idea is that we take in a program that is in bitcode form. It doesn't have to be fully linked. It can be separate bitcode modules. We profile the program, and the main point here is a very simple one. Basically, we're using profiling to identify the hot parts of the code, extracting each of the hot portions, which includes the loop and some functions called by the loop, auto-tuning that portion separately from all the other portions. And so you're basically trying to use this profiling as a way to focus the time or the resources of the tuner on the most important parts of the code. So it's a pretty obvious and straightforward idea. The main question is this enough in practice to really scale tuning to large applications? And moreover, actually get useful performance benefits from that process. So that's really the question we're trying to answer here. And one point I want to make here is that this is not the same as profile-guided optimization. So profile-guided optimization basically is a situation where you're trying to use some kind of performance metrics like call frequencies or branch frequencies or something like that in guiding detailed optimization choices within a particular optimization algorithm. And in fact, you can do that in this process, in this Autotuner if you like. But what we're doing is separate from that. What we're doing here is using profiling to focus the tuner on particular parts of the code. So it's basically to make efficient use of the resources of the tuner. So the compile step here works as follows. What we do is, if you have an application with some number of separate bit code modules, we try to identify hot loops in that application, and we particularly focus on top-level natural loops in functions. This is somewhat arbitrary in the sense that we could have just as well tried to look at all loops, but that would have increased the overhead of the profiling quite a bit. So this is a sort of a simple empirical choice. So let's say we picked two loops, the yellow one, loop 1, and a blue one, loop 2, as the hot ones to tune. We pull that loop out. So we pull, like for example here, the first loop into a separate module, and we also pull out all the functions that are observed to be called from that loop during the profile phase. And one point here I want to make is that we're not using a static call graph analysis to figure out what functions are called, because that can in practice often be very conservative, and you'll get a lot of functions that may not be interesting. Since we're doing this profiling anyway, we just look at what functions were actually seen to be called from that loop during this profile phase and treat those as the functions to be extracted. And so we do that for each of the hot loops, and some of the loops, like the one in the second module here, might actually be called by both loops, and we effectively clone it because we put a copy into each module that we're going to be tuning. So there is some degree of code in expansion here, and I'll come back to that in a moment. So the basic idea then is that we use the profile information to come up with an extraction policy, which basically is a list of hot loops, and for each loop, a list of functions to extract along with that loop. That's what an extraction policy becomes. And so just as an example, our profiler, it's a custom profiler which we wrote, extracts the time spent in each of these loops and the time spent in each of the functions, but also extracts the nesting relationship between them. So we know which functions were called from which loops. And so for example here, you might have a function 1 that takes 100% of the time, and the time is spent 15% in loop 1, 85% in loop 2, and loop 2 calls function 3, which contains loop 3 and loop 4, and that one calls loop function 2, and the numbers here basically denote what fraction of time is spent in each one of these. And if let's say we pick a policy that says you should tune any loops that fall between 10 and 40% of the total execution time, then in this case that would mean picking loop 1, which takes 15%, and loop 3, which takes 40%, but not loop 4, which takes 45, or loop 2, which takes 85. So basically that's how we're focusing the code, and for each one we then pull out the loop along with the function or functions that it calls. This example just shows one function for each one, and that is basically the module that we're going to tune for each of the loops. And the default policy right now is just to extract loops that fall between some min-max range of time. This is not necessarily a particularly intelligent policy. We're actually working now on trying to come up with policies that take into account the code size increase and also pick the loops more intelligently in terms of what might give the most benefit. But so far, all our experiments have been with the default policy. So this approach of extracting loops and then doing auto-tuning can be used for many different kinds of tuning. Just as an example here, the first one we tried is to tune pass sequences in opt. So essentially passes on the LLVM IR, and the way we do that is we take each of the extracted modules, so that's one loop, hot loop at a time along with its functions, apply a pass sequence to it, and then compile it basically with the default backend code generator and measure the performance. And then we use a framework called Autotuning from MIT, which has a very nice set of search heuristics that help you navigate a large search space. And it actually uses 7 different heuristics simultaneously, and it does some very intelligent things in terms of choosing the heuristics dynamically. And if you've not tried that before, I strongly recommend looking at it, opentuner.org, if you're interested in doing any kind of custom auto tuning. It's not even specific to compilers, it can be used for all kinds of different things. So we use that to drive the search process here. And once we're done, we apply this iteratively. So we do this right now for some fixed number of iterations, or in other words, code versions, or you can also do it for a fixed time budget. When either of those is complete, we take the best version we found so far and then compile it with the backend and generate the optimized binary. So this is basically the process of compiling a program. You can think of it as a Clang plugin, except a very expensive one to optimize the code. So how well does all this work? So we wanted to try and answer 3 questions here. The first one is, does this code extraction approach actually allow you to optimize and auto-tune large applications? The second one is, does this extraction process itself hurt optimizations? Because what we're doing is we are isolating parts of the program and only optimizing those separately from the rest of the program. So for interprocedural optimizations, for example, especially cross-module ones, maybe this would actually hurt in some cases. And the third question is, for a particular use of this auto-tuner, like the pass sequence tuning, what kind of benefits do you actually see when you apply it only to these extracted hot loops in large applications? So let me take those one by one. And before getting the numbers, we did the experiments using both the spec 2006 benchmarks and Clang. We've actually also done SQLite 3, although I don't have those numbers with me here. All the numbers I'm going to show you are going to be compared against a baseline, which is basically compiling the program using Clang with -03 and LTO turned on. And for the spec benchmarks, we used an extraction policy of 10 to 85%. For Clang, I'll present the numbers in a few minutes. And the pass sequences that we are exploring are basically described using an Autotuner script, which can in fact repeat passes multiple times. We limit the length of the pass sequence to 150 different possible passes. Not necessarily different, they could be repeated. So 150 passes in total is the maximum number that we allow in searching through these sequences. And we ran the experiments on Amazon Web Services. We only actually used one node in there, so it's a 4-core system. This process can easily be parallelized across many nodes in a cluster. It's not something we have done so far. So all the timings I'll show you have been run on a single node at a time. We could get much more parallelism and speed it up much more that way, and it's something that we plan to do fairly soon. We use the default Autotuner heuristics, as I said earlier, and we limited the search to 1,000 versions for the spec benchmarks, for each of the spec benchmarks. So the first question was, how much time does it take, how practical is it to apply these to fairly large programs? And for the spec benchmarks in particular, I don't show we haven't done an average here because for the tuning time it's not as important, but the time ranges, so these are in minutes, and it ranges from just a few minutes on the fastest one to almost 5 hours for the slowest one here, which is LNC. And so this is a pretty expensive process. This is not intended to be something you do very often, but hopefully it's something that you can do once in a while to choose what compiler options you would use for your program. But the point is that with a single node, we're able to do this in a few hours for a particular application. And some of these applications are quite big, like GCC, for example, is one of these, SQLite 3, Sphinx 3, POV-RAID, some of these are pretty sizable applications. So the second question is, does this extraction itself hurt? So what this bar chart is showing is the performance without any auto-tuning. So this is just the performance compiling the separately extracted hot loops using Clang -03 FLTO. compared with compiling the entire application together with the same options. So the effect is only because of extraction. And what we see is that there is some impact in performance, but it's always a few percent. A few cases actually speed up. And in fact, the average speed up in this set of benchmarks was 1%, so we actually made it faster by extraction. But it's a small enough effect that it could be due to all kinds of effects like code layout, stack layout, many other minor issues like that. The worst we saw was a slowdown of about 2.5% in the Go benchmark. Interestingly, Go actually speeds up quite a lot from auto-tuning, so we're more than able to make up for these small losses. And in fact, that's what we found in practice, that the small damage that you do by extraction is usually compensated for even by very brain-dead kind of auto-tuning. So the third set of numbers here is the performance improvements that you see from tuning the pass sequences. And this is about 16 of the spec benchmarks. We did both the profiling and the auto-tuning, which require a set of inputs. We did that using the train input set for spec. And then we took the optimized program and measured the performance improvements compared with the baseline using the ref input set, which is the prescribed way to do it with for spec benchmarks. And what we see here is an average of about 6.5% improvement across the spec benchmarks. And in some cases, we see much larger improvements, like for example, in Go, as I said earlier, we see over 25%, and in HMMER, we see over 35% improvements from this auto-tuning process. So you're seeing fairly significant improvements in some cases and reasonable improvements overall on average. And by the way, there are a couple of cases where the search itself never finds an option that's as good as the baseline, but we should just ignore that because you can always just use the baseline since you can easily check that it's faster. So we can easily just eliminate this. There's no reason to use a slower version. But we didn't do that. The average includes these negative numbers here. We also did the same experiment with Clang. I'm keeping the bar chart separate because we used different policies. So here we used a policy between 2 and 20%. We extracted 7 hot loops. That's what the policy effectively told us to do. This time we used 3,000 iterations, which took longer. It took almost 14 hours. And we measured the performance using the CT-mark performance measurement thing that has been put in for Clang sometime last year. It uses about 10 applications to monitor performance regressions. And what we see in this case is that Clang speeds up on average for this set of benchmarks by about 6.7%. So we're able to get a fairly noticeable performance improvement in compiling these programs. And in this particular configuration of Clang is about 2 million lines of code. So I think it shows that you can really apply auto-tuning to these programs of this size. And in fact, we don't see any obstacle to doing much larger programs. It just depends on how effective your extraction policy is. If you can find a few hot loops like we did with Clang, then it can easily scale to much larger programs as well. If you have a very, very flat profile, it probably wouldn't work as well. Right? This shows how the runtime evolves. So one particular benchmark, I'll probably skip that slide, but if anybody's interested, I'm more than happy to show it to you offline. So that was the compile stage so far. The evaluation stage, because we're doing explicit measurement, is one significant bottleneck in this process. It turns out that there's quite a bit of redundancy in the experiments, because let's say you're tuning, if the yellow parts are the loops you're tuning, and you're tuning on the fourth loop in this case, every single measurement you're going to do in those 1,000 iterations or 3,000 iterations or whatever is going to execute the program from the beginning all the way to the starting point of this, and then measure this one loop. And that's completely redundant. There's no real benefit in doing that for most loops, and I'll come back to that in a moment. So Yishen actually came up with a very nice automated way to checkpoint the program simply by forking the process and then measuring just the hot loop itself, basically measuring every version of the hot loop generated by a server. So the server generates these versions using OpenTuner. And it greatly speeds up the process. That is not even reflected in the previous numbers I showed you. And by the way, has some restrictions, so the loop itself can't do it can't be synchronizing with external code, it can't be doing I/O with side effects and things like that. So there are some restrictions, but for many computationally intensive loops, it works just fine. So that was compile and evaluate, and then let me briefly talk about the search strategies which are defined by some kind of plugin. So the ones we've looked at so far have been searching path sequences. We've also done some very preliminary experiments with stack layout and code layout. We saw very small improvements with that. And I suspect in practice that profile guided layout choices will probably do better or do as well. So it may not be worth doing all the investment with auto tuning, but that's a very preliminary finding. So I'm not sure if that's really true in practice or not. We're looking at some other ones right now. So one thing we're looking at is the inlining heuristics. Right now, Clang and I believe GCC also basically applies some particular strategy, like for example saying, let's inline functions if they fall above a certain threshold. And it's sort of a blanket strategy that's applied at all call sites. But in fact, inlining can have different benefits depending on the register usage of the caller and the callee, the opportunities to maybe hoist code out of the callee in some enclosing loop and so on. And these are quite dependent on the context of the call site. And these are not taken into account in many inlining algorithms. So what we're trying to do is to try to learn these kinds of heuristics in a way that can be driven by different call site characteristics. Another one we're trying to do right now is to do data structure layout exploration. So basically define a search space of different data structure transformations and then explore that using the auto tuner. We're also interested in looking at loop schedules, GPU mappings for heterogeneous systems, and these are things we've not started on yet, but I hope to see that happening soon. So we have a bunch of ongoing work and some plans for future work. I'll just go through this fairly quickly. On the infrastructure itself, LLVMTuner, the system itself, we are looking at a more intelligent extraction policy that takes code size into account. We're looking at doing install time auto tuning when you have much more detailed information about the particular target architecture on which you're running each program. And the main thing we need to do here is to try and make it much easier to ship programs as bitcode. And so we have a project called LLVM that is looking at shipping programs as bitcode. There's many other benefits of that. This is just, auto tuning is just one of the things you can do with LLVM. Another thing that I would really like to explore in the near future is to enable application developers to use application-specific or program-specific tuning policies with their applications. So for example, when Atlas explores loop tilings, the Atlas library authors shouldn't have to go write scripts to do transformations on their loop nests to explore the search space of different tile sizes. It's a compiler transform. It should be much easier than that for them. And that's just a small example of the kind of thing you could make much easier for application developers. And that's something we're hoping to enable with LLVMTuner. It's also pretty obvious as a next step to integrate with both PGO and LTO. Thin LTO in particular. Thin LTO effectively does a similar kind or analogous kind of extraction to focus or limit the amount of resources used by LTO. And then on the, we're also looking at a number of different use cases for LLVMTuner. I already mentioned inlining heuristics and data structure layouts. We are starting to look at how to tune the mappings of kernels to devices in a heterogeneous system. Like for example, when you have GPU and host and maybe even other devices at the same time. And we're also doing some work on FPGA design synthesis, which I'll be happy to talk to people about if you're interested. There are some fairly closely related systems. I'll just say a few words about them because I'm getting close to time here. But Milepost GCC is probably the best known previous system that explored different kinds of path sequences. They use machine learning to do this. That particular system was specifically focused on path sequences, whereas with LLVMTuner, we're trying to be much more general in terms of what kinds of tuning strategies you want to try. And also, one of the main goals we have been focusing on so far is how to make it easier to scale to much larger applications. OpenTuner is this framework that I just mentioned that we use, the one from MIT. This is a really flexible, powerful system. It allows you to define tuning strategies for programs. and define them as Python scripts and explore a wide range of them. And we've built on that directly in our work. They have not actually explored any particular ways to make auto-tuning scale to larger systems. And then there are a couple of other systems that are not quite auto-tuning, but they're related in some ways. So Cere, I'm not quite sure how to pronounce that, C-E-R-E. They do extraction of hot loops. They call them codelets. And then they can use that for a variety of things. Their main focus has been on using that for performance prediction. They don't actually do interprocedural optimization because they don't extract hot functions with the loops. And I think that's one of the key things that you do have to do if you're doing code extraction in this way. And then there's a framework called CK, which is a pretty rich framework for doing very reproducible experiments. They have actually used that to do some auto-tuning, but their main focus has been on reproducibility so far. So that's pretty much the end of my talk. Just to summarize briefly, what we focused on so far in LLVMTuner is a code extraction strategy to make it easier to scale expensive auto-tuning techniques to much larger realistic applications. And so far, at least, the results have been fairly promising. We can do fairly large applications and we do see useful performance benefits, even with a very generic pass sequence tuning kind of approach. I think the more domain-specific, application-specific tuning strategies can be far more powerful and give much bigger benefits. So our goal here is to develop a framework in LLVM that makes it easier for application developers to design, or compiler developers to design more focused tuning strategies for their systems. And with that, I'll stop and happy to take any questions.
Two short questions, but basically related to investment of time.
Yeah.
So first, is this system can be used as a drop-in replacement for compiler? So you have your main file, whatever, and you just replace clamp with clamp tuner?
Yeah. In theory, it could. I mean, in theory, in the sense, it doesn't do it today, but I think with a small amount of engineering, you could easily make it happen, because it looks like just running Clang, but in 3 steps. We basically do the profiling, and then we do the tuning. It's really two big steps. So it's profiling and then the tuning. And it's separate programs right now, but you could easily wrap it up into one program. So yes.
Okay. And second, you mentioned investment of, what's the figure, 6 hours or something?
Yeah.
Whatever figure on one of your slides.
Yeah.
So
the time, the auto-tuning time. I think this was the first slide.
Very, very first slides.
This is the first bar chart.
No.
This is the speed up. This is ignoring tuning. What is the damage done by extraction? And this is the actual performance improvements for spec. And then I have similar ones for Clang.
Whatever. The time investment, is it investment of machine time or human time?
Oh, it's very much machine time. Yeah, the human time is just our time creating the system. For an end user, it's fully automatic. Yeah, it's totally machine time.
I think I missed a few comments on the program-specific tuning on the application, which you mentioned on the last couple of slides.
Yeah.
Could you elaborate a little bit on how you can envision that? Would it be, so you mentioned like one flexible system at the end. Would you configure that, or how would you configure that? And would it come to DSL?
Well, so the way that the system works is that you can use you can write a Python script as a plugin to describe a search space, and typically what you would do is at the application level, you would probably have some parameters that you want to tune, and it might be tiling parameters, it might be algorithmic choices. There are a wide range of different things that you could try to tune that way, or it could be, sorry? You could pass it as, you would have to somehow structure your code so that there would be a knob to control which version you're using, or what numbers you're using, or whatever. So the code would have to be structured to make sure it can be tunable, and then otherwise it's writing this kind of Python script to describe the space of tuning options. And the tuning options can be numbers, they can be sort of an enumeration of different choices, various things like that. And some of that actually OpenTuner already provides. So we're basically building on the OpenTuner capability to describe search spaces using Python scripts. See a couple of hands up here. One here. Oh.
Can you comment on the effect the input data makes on the auto-tuning decisions? I mean, you had this graph that you on the speed up results on the spec where you have the input split between train and ref.
Yeah. Yeah.
How much do you think that really generalizes over data?
I think that's something that really depends on how representative an input set you can provide for doing the profiling. If you have dramatically different behavior in production versus what you use in tuning, you might not see the benefits that you'd like. But it's pretty random in some sense, because in the sense that if you're representative, it's not random. But if it's not representative, it's pretty random. You might actually see very good benefits even if the application behavior is very different in production versus in the tuning. But there is a dependence on the input, yes.
And I guess it gets much worse if you do inlining or data structure layout or kernel mapping.
Worse in what sense?
Worse in the sense
Oh,
that
yeah.
the data dependence.
The data dependence, right. Yes, absolutely. It can become, you can become more sensitive to data to which inputs you tune for. That's absolutely right, yes. So in fact, for example, Atlas literally tunes for different shapes of matrices because it makes a huge difference in matrix multiply what shapes you use, right? So that's very much part of it. But there you expect the programmer, the application person to have some understanding of this issue. Otherwise it wouldn't work well.
Thank you for the excellent talk. I would like to have a bit better understanding of profiling that you're doing. Did you try to compare prediction of performance and the experiments that you do for offline loop and performance of the whole application? What are variations? And so basically, can you model correctly something like cache effects and other microarchitectural features?
Are you asking about profiling or are you asking about performance prediction, the performance measurement?
Performance prediction that you use for auto-tuning, basically.
Yeah, so we do not do any performance prediction right now. So in this phase of let me just go back to the slide that shows the overview. Sorry, where did I put it? Oh, it's later, sorry. Tuning hardcode, this one. So at this point here, we are basically compiling each version and directly measuring the performance on the system. And so any cache effects and other things are explicitly measured, but obviously it's a very expensive process, right? We would very much like to do some performance prediction. And in fact, I recently wrote a proposal that included doing some performance prediction for exactly this reason. It's very hard. The problem is that there are so many interactions between both compiler passes and also between different performance effects in the underlying system that really doing any kind of reliable prediction is very hard. Now, it might be possible to make correct decisions even if you don't have accurate predictions. So there is some hope, but I'm not sure how well it'll work. Any other questions? Okay.
So, how much code do you actually extract? So after loop extraction, after loop extraction. So how much is left? Is it like 1%, 10?
So I don't know the number in terms of percentage, but for example, in Clang, I said we extracted 7 hot loops. I don't know how many functions were part of those loops, but really it was a very tiny fraction of the 2 million lines of code. So I don't know offhand the number, but it was very, very small.
Less than 10, something like
that. Oh, way less than 10.
Okay.
Yeah. I would guess 2 million lines, I would guess less than 1%. That's my guess. And I should know that number. We got the Clang numbers after I left for Germany. So they're very fresh, or they're kind of fresh off the bat.
Yeah, but just
I can get the numbers.
because it
Yeah.
makes a difference.
Of course, yeah. Right.
Quick follow-up question. How do you actually extract loops? Is it done?
Oh, it's LLVM. It's the extraction passes in LLVM. So we basically extract, because we have to extract portions of functions, we're using there's a function extractor and a basic block extractor. So, yeah, nothing magic in that. Any other question? Okay. Thank you.